Welcome to Neurosalience, the OHBM podcast.
Welcome to the Organization for Human Brain Mapping Neurosalience podcast. I'm Peter Bannattini, and here I discuss brain imaging with scientists from all over the world. Today I'm talking with a scientist who's just down the hall from me, Dr. Gang Chen. Dr. Chen is the go-to statistics guru for the fMRI community at the NIH and a well-respected scientist worldwide. He's a staff scientist in the group that develops the AFNI software package. I'm interviewing because he's my favorite fMRI statistician. Technically, he's an applied mathematician. In the past 7 years, he's written a series of insightful papers bucking the status quo in fMRI processing, essentially saying that we are throwing away too much valuable information by thresholding our data, relying on overly simple and rigid models of the hemodynamic response, not mapping effect sizes, and using center of mass measures to describe clusters of activation. He backs it all up with a rigorous approach characterized by all good statisticians. He's a master in the art of casting a wide net to capture useful data without taking in artifact and noise, finding that sweet spot in data reduction to balance utility with sensitivity. In this podcast, we discuss his perspectives through these papers, which I believe are so important, yet not known well, much less embraced by the field. I hope you enjoy it. And today we have Gang Chen, who's a good friend of mine, a colleague from the NIH. Actually, Gang was on this podcast a long time ago, and we were talking about AFNI. He's part of the AFNI team. He's been with that team for, I guess, since 2003. And one thing about Gang, just really quickly, that I want to mention is that he's a applied mathematician. Some people might think he's now moving more towards a statistician, but at the same time, I really like how he thinks broadly and deeply about the signal itself and how we're doing our processing. And that everything he does is correct, but at the same time, he also isn't afraid to question how things are generally done in the field. So, Gang, thanks for coming on.
Yeah, thanks, Peter, for giving me the opportunity to discuss some statistical issues in neuroimaging.
Yeah. And before this podcast, you sent me some papers of yours, 5 of them that were just really outstanding, and we'll get into that as we discuss. But and we'll talk about 5 topics as well. And the first one is the issue of thresholding. Second one is the issue of multiple comparison adjustments. Third one is on effect estimation. And fourth one is on model building. Finally, the fifth one is the role of statistics actually in neuroimaging. And so, but before we begin all that, I just want to talk a little bit about you and how you started. So when did you first, I guess maybe early on, you just thought in school, you just had an affinity for math and you just wanted to get into that? Or did you have other interests? Or like, when did you decide that you wanted to be an applied mathematician?
My training was in applied math and statistics. So when I came to the U.S. at the University of Arizona, the program was actually in ecology and evolution biology. But my specific research topic was pretty much applied math. Yeah. So I was in the lab of Dr. Arthur Winfrey. He was a great biologist, but he also had a strong interdisciplinary spectrum. So a great intuition. So my research during that time was applied partial differential equations to excitable media. Excitable media, it's include like heart muscles or even brain. So it's explain the action potential, right? So both in neurons and in heart muscles, how it propagate through the muscles spatially, right? So that was my PhD thesis. So after my graduation in 1989, I joined an industry, actually a startup company in Princeton, New Jersey. was interesting because the idea was to apply the work in graduate school to develop some software, then simulate the problems in the heart. For example, arrhythmia, fibrillations, right? So same idea using partial differential equation. The idea was to develop software so the pharmaceutical companies can use the software to simulate when something goes wrong, how a drug can intervene to break up that problem, right? So fibrillation, I mean, the heart usually is a periodic 1 hertz, right? So there's a pacemaker, so they get a signal from the brain, they periodically then contract, then relax. So the blood is pumped to the whole body.
Okay.
So that was the idea, but I think looking back, that was too ahead of time. Even 20 years after that, then that's still not feasible. I mean, so 4 years after that, then the burn out of the money, so the company disappeared. So I had to find a job. So that's why I landed in the AFNI team. So Bob during that put an advertisement on Yahoo. So Google didn't exist at that time. So I came to NIH for job interview. So before that, during my work was pretty much in applied math. So, but he was recruiting a statistician, right? The main question he asked me, what's the difference between a paired t-test and a two-sample t-test? So I haven't had a lot touched the statistics for over 10 years. But fortunately, I passed that exam. So it was quite interesting. That's 20 years already.
Wow.
At the beginning, I had to learn a lot about neuroscience, right? Because my job is supposed to, consulting, help people using AFNI and develop software, new modeling approaches. So one couple of things that at the beginning, while I was learning neuroscience, I was a little bit surprised to see, because during that time, or even maybe it's still the case, the popular approach is in fMRI is still pretty much a t-test and the regression. So the users usually had a problem running slightly complicated models like ANOVA, right? So ANOVA, you have experiment designs. Usually you have different factors. You have groups, right? Patients versus controls. Then you have tasks. You may have incongruent versus congruent. You have different modality, right? Even it's a visual condition or it's auditory, right? So you have different factors. How do you run such a ANOVA? During that time, there wasn't not many programs available. So that's one thing I was surprised. So I helped to develop a couple of programs. So extending to that work, then the data structure can be complicated, can be correlated. Then you may have one missing data. So then I extended the ANOVA program to linear mixed effects model. So that's a couple of other programs. Later on, there's a naturalistic scanning. So the data structure a little bit even more complex because you calculate the correlation between a subject pair, right? So those pairs are correlated to some extent. How to parse T-cell part that correlation structure. So that's another part of interesting work about the hierarchical model.
Yeah, I know that aside from all the those studies that you've done, you've always been, for the last 20 years, I know that people in my group have constantly gone to you to ask any sort of question and, make sure they're doing something right, or and it's always been incredibly helpful as far as that's concerned. And I think that through that process of helping people and then learning about the information, your views, I think have been refined and have changed over time as well. Yeah, I can't believe it's been 20 years. So over that time, so I've gotten to know you as well, but also at the same time, just reading your recent papers. You've sort of come out with some, technical papers, but sort of couched in sort of an opinion about things. And I really find, your perspective extremely refreshing, because it's not only, it's based on, it's rigorous, but at the same time it's creative, and I feel I was trying to come up with a theme that it follows. And the whole idea is, and you mentioned it several times in your paper, but I really do feel that it's sort of minimizing information loss in the data, sort of along the lines of, fMRI data is so rich and so complex. And what we basically try to do is reduce its dimensionality, reduce, what we're looking for in the signal such that we can actually say something. And so we want to try to put it in some sort of framework that we can say something. But in the process, we lose all this other information that might, be very, very relevant to what we're doing. So I've been, when I was reading your papers, I would be like, yes, this is exactly right. And I think that it's really important because I think there's a blind spot. I think, and we'll get into the discussion, but I think it's a blind spot in the field that you have this. Most statisticians don't really. A lot of them know the data well, but they're trying to find something that is defendable. But at the same time, and most neuroscientists, when they're starting out, they just want to do something that the reviewer will be okay with for the most part. I mean, we all do that. But somewhere there's a blind spot of there's all these things that you could do and that you should be doing maybe that might help a lot. And so, okay, why don't we start out with the discussion on thresholding? That's one that's most easily accessible. And, obviously people might argue that, well, you have to threshold your data, based on a statistical test. That seems like a reasonable thing to do, and just show these threshold responses. Otherwise, what do you show? How do you compare? Is it truly necessary? Why don't you, and also just to mention, you have a paper in Neuroimage that came out in 2023. So just recently, first author was Paul Taylor. Highlight results, don't hide them, enhance interpretation, reduce biases, and improve reproducibility in Neuroimage in 2023. So why don't you talk about thresholding?
Right. Yeah. Before we talk about the thresholding, let me step back a little bit, talk about a little bit historical development.
Okay.
So we know fMRI is a lot of data, and it's very complex. We still don't know the components of the both signal, right? So the argue there's neural activities, there are vascular active physiological components. I mean, scanner noise. I mean, we don't even know how to separate those, and we don't know the percentage, right? So, I mean, maybe region dependent. So we don't know. So that's a plus. There are modeling strategies, right? So voxel level, individual level, group level, right? So then there's a multiple comparison issue, of course.
Yeah.
So historically, I remember, let me trace back a little bit. First of all, there's I think around 2009 or 2008-ish, there's this double dipping or circularity, or some people call it voodoo correlation, right?
Yep.
So Edvo, I think, started the issue, right? So during that time, the common practice, you run fMRI analysis, you find a so-called significant region. You pick a voxel, then either you use that voxel, or you draw a sphere with, for example, 6 millimeters. Then you correlate that with behavior data. So that Edvo's paper basically argued that approach is you have the selection bias problem.
Yeah.
So you end up with unbelievably high correlation value.
Yep.
That was Edvo's. Then Nico Corcascote also extend that to classification, right? So if you pre-select the voxels in the brain, then you may exaggerate the classification accuracy. So I think looking back, this issue, I think, well, in the field, I think this issue resolved, and I fully agree. So this is a big problem. But then move to the next controversy, the data assignment, right? So that was a big story. Data assignment, I think, were around the same time in 2010. Craig Burnett, I think in Dartmouth. So they scanned this data assignment for some period of time, then analyzed it. Then I found a cluster of 3 voxels, 3 by 3 by 3 isotropic voxels.
Oh, this is the clustering conundrum. This is the clustering controversy.
Right. Yeah.
Yes.
So then this is bring up, I mean, the issue of how can we trust these statistic significant results, right? So that brings up the urgency, how to handle multiple comparison, right? But so then that brought up to the next controversy. I mean, well, I call it controversy, but Anders Eklund's paper 2016, cluster failure. So that basically an extension of the data sampling issue, trying to make it more vigorous. So they around that time or before that time, there have been, it's the multiple current issue have been around for a long time, or at the beginning, right? So it's quite intuitive. This also is tied to this traditional statistics. Traditional statistics use p-value, right? What is p-value? P-value is sort of an indirect evidence. What does it mean when I say it's an indirect evidence? So you have the data, then you pretend there's no signal in the data. So you make that a hypothesis called the null hypothesis. You pretend that there's no signal, then check your data, then see the result. The result, how surprised you are, how inconsistent the data is with that null hypothesis, no signal at all. So that's I call the indirect evidence. So the traditional studies say there's a p-value. That p-value is there's a line you draw in the sand called the 0.05, right? So that's about 100 years ago, Fisher is a pickup that is 1 out of 20.
Yeah.
Well, so then, in the field during that time, right, because the data sampling, then have basically two approaches to handle that. Well, there are more. There's, for example, false discovery. But the major one is family-wise error. The idea is pretty intuitive. As this indirect evidence is that we assume there's no signal at all. Then suppose that's the case. What is the chance you get the result, right? So then if it's a cluster, the chance would be less. Would be low, right? So the form spatially among the neighboring voxels. So one approach is you first select the p-value, for example, 0.01. Then you find the cluster size. Then that cluster threshold would give some sort of the whole brain level family-wise error. So that's one approach. People call that parametric. Another approach is you don't pick up one particular voxel-wise p-value. You pick up a range. For example, from 0.05 to 0.001, for example. Yeah. You got p-value range. Then you find all sorts of clusters. The cluster size may vary, but the point is to control the overall family-wise error at the whole brain level. So that people call that a long parametric approach because it adopts their permutation method. So those are the main approaches. So the Anders Eklund, and his colleagues, at that time, they examined those two basic approaches.
Yep.
So how stringent they are. So their findings are basically the parametric approach is not stringent enough if the voxel level p-value is 0.01 or above. So because of that finding, nowadays, we are basically have to adopt either the parametric approach using voxel level p-value 0.01 plus the cluster threshold to achieve the whole brain family-wise error. Okay. Or you can adopt the non-parametric approach. That because that passed the Eklund's examination, so that is considered stringent.
So let me just interject here. I remember when that thresholding thing came up, and I'll take a very different view rather than describe the technical aspect of that. I actually said, well, if your conclusions depend on how different the cluster size is, that's actually a very oddly weak study. Anytime if your conclusions actually really do depend on whether your cluster is, 100 voxels or 110 voxels or whatever, you're sort of, right. That's a sort of a fragile sort of result. And so most of the results, the actual conclusions weren't changed. It's just that some of the nuances were a little bit different. But yeah, okay. Sorry for interrupting you. But rather than go into a detailed description of clustering and thresholding, your paper actually talked about, is it even necessary? And what should you do? The threshold might be it's still somewhat arbitrary since you don't really model the noise perfectly and you don't model the signal perfectly. So
yeah, we can talk about the why I consider that's a lot of reasonable approach later, but I want to delay that discussion. I want to give this a historical development. because this is leads to the next controversy. That's 2020, this LARPS project. So in Nature,
What project? The what?
NARPS.
The NARPS, right? The NARPS study,
Yeah,
where they
NARPS study.
where they scanned like 90, where they had 90 or 80 different or 70 different labs analyze the same data set. Yeah.
Right, exactly. So that it was an interesting result. I feel very intriguing in various aspects. So even in that abstract of that paper, they have two conclusions. The first conclusion, they call those 7 teams had a sizable variation because they had a lying hypothesis. Only one hypothesis, 80% of the teams tended to reach the same conclusion. But the other, I think the 3 hypotheses is the opposite. Only 5% of them rejected null hypothesis, basically show that the hypothesis, the research hypothesis is supported by the evidence. The other 5 hypotheses, basically it's a sort of a half, or around half-half, so inconclusive. So based on that results, that's a dichotomized results. Remember, that's based on stringent threshold, based on cluster level, Hopin level, family-wise error of 0.05. So their conclusion, okay, there's a reproducible crisis problem because across 70 teams, they couldn't reach only one hypothesis, 80% of the team, right? So this is considered a hypothesis reproducible crisis.
So it's interesting. If I could just interject, I don't. To their credit, I agree with that. That was sort of like the interpretation, but their thrust to that paper was to try to say, oh well, you need to, maybe have different groups, come to a consensus, and then that's the way forward to have open and transparent. But you're right. I mean, and quickly the media picked it up and saying, wait a second, all these experts analyzed this data and they got totally different results, which is definitely not, I don't think, the correct message. But anyway, go on. Sorry.
Well, yeah, that's why it's a pretty interesting paper. So they had a second conclusion in the abstract. The second conclusion, if they don't threshold the result, simply based on the statistical value, nothing about the brain response magnitude, just the statistical value. If you don't threshold them, then they say the 70 teams, they do have significant consensus.
Yep.
Okay, you have 2 different conclusions.
Yes.
First of all, why only the first conclusion is broadcast widely and emphasized in social media, in all the citations afterwards.
Yeah.
Why? Is this a selection bias? I mean, this you pick up one, right? But there's another conclusion. How do we reconcile those 2 conclusions? That's another interesting point. But why people just simply pick the first one, totally ignore the second conclusion?
Well, that's human nature. If it points out something that's potentially alarming, you pay more attention. If it's something that's like, oh, it's good, then it's like, okay, well, it's good.
Well, it fits the reproducible crisis narrative, basically. It's that fits that canonization.
But that's actually maybe we'll even start there. I mean, that's actually a really important point, that if you don't threshold, and you even showed this as well in your paper, that if you don't threshold, I mean, it's like saying, okay, well, if you don't threshold, you still have this effect. It's just below threshold, but it's sort of like it as opposed to having like these little islands. If you have 2 little islands of activation that are a little bit different, of course they'll be not the same. And so then, but if you have like these islands that are connected by, that below threshold, then they're overlapping, and there's contours in the data that's below threshold that shows a huge agreement with the data. So why don't we talk about that? I mean, that's actually kind of the point of the first point, I guess.
So the paper, the NARPS paper, I think that in the end, so they emphasize this or they call it analytical flexibility, right? So, I mean, that begs the question: should we blame we have too much flexibility in the field, right? Is that's an interesting question. I mean, some people may argue, okay, flexibility is good until it's not. Really? Is that? I mean, how can we? Then should we reduce the flexibility, or should we standardize all the pipelines to reduce to only one software package, or only to reduce the options? So
Yeah.
that's basically big. I mean, we need to reflect. But there are other perspectives, as you brought up. It's about the thresholding, right? So how do we deal with the thresholding?
And I totally agree with you that that is an interesting tension in the field, is that you have standards, but at the same time it's evolving so rapidly and we're getting better understanding, and that you can't dictate, you know, one package, this is the way to do it. I mean, that would be horrible, because everyone feels that there's so much more information there in the data that you have to keep on evolving the packages. And so what do you do? I mean, what do you do with this data? I mean, the way to actually change the field is to, obviously people don't necessarily read, like you said, the second paper that says, oh, if you reduce the threshold, everything looks the same. But they would read it if you actually produce some really cool results with this different approach, that you couldn't see otherwise. And so maybe that it needs to be sold by the results.
The question is how to achieve reproducibility. One approach is, I mean, as that looks like the currently practice in the field, is to keep as stringent as possible. That's just the thresholding, right? So that's one approach. Another approach I prefer is I call it integrative, more inclusive. Don't adopt the stringent thresholding. Why I'm thinking that would be a better approach. I mean, look at even I don't know if this is good to talk about. There's I think two good examples about the thresholding outside of neuroimaging. One example is about in psychology. So I mean, during the past few years, there's a dispute about controversy about power posing, implicitly priming, right? So there's a lot, because those papers in there, they show the p-value is less than 0.05, sometimes even lower, right? Simply because the p-value is small, then the results are sort of trustworthy and believing. So there's this, I mean, famous paper by Daniel Kahneman, right? So thinking fast and slow.
Yep.
I mean, looking back, those results are not cannot be replicated anymore. So, couple of two chapters, I think he may wish to rewrite because.
Oh, really?
Simply because the p-value is small, that doesn't mean that's a strong enough to believe it. So another example, the opposite is that even if the p-value is greater than 0.5, does that mean it's not believe it has no value at all? So the example is 3 years ago, we are still during at the beginning of the pandemic. So at NIH, there was this clinical trial about remdesivir. I think the drug had showed some promising result, but
Yeah.
one index, I think it's about the mortality rate. It reduces the mortality rate, the patients versus control. I mean, the hospital, versus a placebo, the drug taker versus a placebo. The mortality rate reduced by 30%, but the p-value is 0.059. So it cannot survive the threshold. So when Dr. Anthony Fauci was in the White House talking to the reporters, he struggled a little bit because of this p-value thing. So he used the phrases like tended to, I mean, lenient
Right.
toward to significance. So I mean, this shows the p-value 0.05, how how in the field people how struggle with this. Simply, it's a convention, right? So, but
Right.
why?
But it also makes an assumption about the distribution of the noise and the signal and everything like that. And there's certain things that behavioral studies, maybe you can do that better. But well, just focusing on your paper here, you show, I mean, and this is what we do all the time with our data. We actually, we make a threshold, we look at it and we say, oh, what's, and usually a skilled fMRI practitioner will play with the threshold. We'll look at it and we'll lower it and say, oh, well, that's interesting. It's kind of, then you might look at the threshold and say, oh, there's some asymmetry maybe it's between left and right, language production. And then you lower the threshold, you say, oh, no, they're kind of, there's other areas that come up. It's less, but it's comes up. And you actually, Paul and you propose and that, you have your threshold, but also you kind of show it in a translucent sort of way that you can actually show all the data and sort of give people a better sense that you can't really capture with the statistics, but completely. fMRI data is unique in the sense that you draw a lot of information by where it is, and you know how to interpret what artifacts are, and if there's like all this stuff on the edges, edge effects might be very significant, but everyone who sees them knows, oh, that's not significant because that's an edge. So people learn these heuristics by allowing sort of data through in a sort of translucent way. I mean, it seems like it's good in that regard.
Exactly. So let's associate with the issue. What's the role of statistics, right? So should we use the statistics to police the result reporting, to gatekeeping the results? But another related question is that, do other pieces of information matter? Well, just for example, using the data sampling result. Yeah, there's a cluster there. But should we just fully trust, use the statistic alone to make a decision? Well, there are other pieces of information. For example, that 3 voxel is in the brain cavity. I mean, does the anatomic structure matter? I mean, to give us more information, we simply just use the statistic alone to make a decision, right?
Right.
Another way can argue that it's just one segment. I mean, nowadays we need to group analysis. That's one segment. Is that generalizable? Also, there's a previous study to support that. I mean, they're all pieces of information. We don't just use statistics itself. Yes, statistics is one piece of information, and evidence is always continuous, right? Evidence is the evidence, regardless the strength of the evidence. Currently, there's an open science movement, right? So we emphasize transparency and full result reporting. So that's why you mentioned that our suggestion of a highlight but not a hide approach. So that approach, I think, is more, we consider it's reasonable because, yes, you can emphasize you consider as a strong evidence, but you don't have to hide the rest, right? So whatever the threshold you adopt is to some extent arbitrary. It's you would call it a line drawn in the sand.
Yep.
Right? It's arbitrary. What the current practice, you see those nice, clean, colored blobs. Is really that's the full evidence? That's not. It's that's a little bit. To me, it's not transparent, right? So all evidence is evidence. It's in social media. It's in newspapers. You see those nice blobs. Sounds like give people impression that that's all the evidence we have. It's so clean, so pretty, but that's not the full results.
Right.
So that's why it's the NARP's paper. The first conclusion is misleading because you dichotomize, you hide the rest, regardless. So it's a little bit irony to me is that people try to pursue the stringency, right? So that the hope is to improve reproducibility, but in the end, you hurts the reproducibility because it was misleading results.
Yeah. And that's still information as to why are they different enough that such you make a threshold it doesn't show up. That's an interesting question, but let me just keep this going here because there's several other really, really good points that you bring that you have written about. And that is the idea of modeling sort of trying to model the hemodynamic response variability. Everyone sort of uses your canonical hemodynamic response, they convolve it, and they think they're good and they're done. Whereas obviously there's so much information that you get from it. You have a nice summary in one of your papers, where the peak height, the post undershoot, the width, the latency, the initial dip. And so you actually, and I just want to try to understand what you mean when you talk about this. So just to back up a little bit, before I get into that, well, anyway, let's just talk about the hemodynamic response because that sort of leads into another result that I always like to bring up. When I did this paper with Javier Gonzalez Gasillo, that we averaged for 9 hours, And the null hypothesis actually is potentially not existent, because you do that if you lower your criteria as to what the shape of the hemodynamic response should be. If you average enough, you see pretty much the whole brain active in different ways. That's in a time-locked way. And you showed this as well with less data, but maybe that can tie into the hemodynamic response. You try to do a sort of a spline sort of fitting, and you do that on a voxel-wise basis. So why don't you talk a little bit about that?
Yeah, that is I consider it's a very interesting approach to improve modeling. But do you mind if before we talk about that, I want to still linger around about the thresholding issue?
Sure.
Because there's the important problem of a multiple comparison, right? So the data set is tied to that, the cluster fitness to that. But why that whole brain, the current approach, cluster approach, is problematic to me? I think there's this, famous line by George Box. They say all models are wrong, some of them useful.
Yep.
But I want to refine his saying. I think all models, of course, are wrong approximations. But another equally important is that to realize what exactly they are, the assumptions for each model, why they are wrong, to what extent. So the current approach, the model approach, is called a massive univariate approach. It's each voxel, suppose we have 200 voxels, we build 200,000 separate models, one voxel per model. Of course, this is intuitive, and this is because it fits the available tools and also computationally scalable, right? You can do pretty much most of the analysis in minutes or hours, right? So for those reasons, that's why we adopted this massive univariate approach. But we need to realize that modern approach has some approximations and assumptions. One big assumption, problematic assumption, is that because we assume there's low information shared across the brain, right? So that model, there's low connection among those voxels. But in reality, we do have some information. For example, we know the Boden response is at most a few percent single change. That information, the range we know, that's one thing. Another thing, maybe that's a question for you, Peter. Suppose I have this brain response in the brain. I plot out the distribution of all those voxels, the brain response. What kind of distribution would you expect to see?
If you had a brain response and you have a distribution of all the active voxels in the brain, or
well, all the voxels, regardless they're activated or not, we don't know. We just based on the model, then we find the response, estimate those.
Yeah, I don't know. It's right. I mean, it'll probably be
Well, let me reframe it. Would you say it's uniform everywhere, or it's more centralized, symmetric, roughly symmetric? Which one, the former or later?
I would say it's asymmetric. I mean, I would say it's
surprisingly, it's roughly symmetric.
Oh, it's
it's probably most voxels are close to zero. It's
okay.
Yeah,
all
so small percent of probably around it's around 1% or less. So usually it's roughly symmetric. So you can usually use normal distribution to approximate that.
Okay, even with activation, so you can have a normal distribution of. All right. Okay.
Right. So I have tried this for several data sets. That's pretty much the case. But my point is the current approach, that kind of information, the range of the brain response and the distribution is not in our current modeling approach. Because the current approach, you 200,000 voxels, you have 200,000 models. Those models are totally isolated from each other. So in the end, we waste a lot of information simply because we ignore that. So because we have those many separate models in the end, that's why we have multiple comparison problems. That problem, people solve it by just using the local information, the neighboring voxels, they're related. So that's why we use the smoothness to try to reduce the penalty. But that's not good enough because that's not part of the model. That's why I call it a band-aid. It's a post hoc. It's something afterward. So ideally, think about the brain. We have a hierarchical structure. We only have one brain. In that brain, we have multiple networks. Each network has multiple regions. Ideally, we should build just one model. that model contains all the hierarchical structure of those levels. That model would use the information I was talking about, how those regions, those networks, they can share the information.
Yeah, I'm not sure. Actually, I sort of lost you there a little bit. So you're saying, so I mean, as far as the practical application here, so as far as building, so you're talking about building a model of the hemodynamic response.
Oh,
Or-
not in response yet. Let's delay
Okay.
that. Let's just say the big picture.
Okay.
Big picture, we have networks, we have regions, then we have voxels at different levels.
Right.
So we, at least conceptually, we could build just one model, not many models, as many models as voxels. We don't do that. We
Right.
just build one model that contains all the hierarchical structure of the brain.
Yep.
So
Okay.
that is how the brain works.
Okay.
We only have one brain. Whatever we respond to stimuli, we only, I mean, the brain act in a hierarchical way, orchestrated one way.
Right.
It's not
Right.
each voxel acts alone.
So when you say build a hierarchical model, then you so this reminds me of when I was reading in your paper how to deal with, if you did, as opposed to reporting center of masses of areas, you look at the overlap with parcels to some degree. But I mean, I don't know if that was when you say build. So how would you, practically speaking, how would you do that?
Yeah, conceptually we should do that, but practically, yes, we don't have the computation power to do that. At least to a lesser extent, during the first few years, we tried this just at the region level RI. Suppose we have, for example, 100 RIs. We build just one model, not one model per RI. We just one model include all the RIs.
Yep.
Then we assume those RIs follow normal distribution, simply because then we have one model, there's no multiple comparison issue.
Okay.
Because the information is shared across those regions. So that immediately we improved the efficiency of the model.
Okay, so I think you probably, I just want to try to keep this a way that we can get an actionable message from the fMRI users. So I mean, so when you're talking about this, what should we do? What should we do? All right, you're talking about models, you're talking about hierarchies, you're talking about correlations, but what should we actually do in this regard?
Well, we can still continue to use the traditional approach at the voxel level, right? But we need to keep in mind that wastes a lot of information. That's why we have multiple cancer problem.
So let me I'm purposely just trying to stop you here, because I think that you're using jargon that people have different views of. So you're saying, okay, when you talk about a model, let's even back up completely here. When you talk about a model, what are we talking about here? We're talking about, so we do our experiment, we have our data. What's the model? Are we modeling what are the aspects of the model? Just so we have something tangible here to go from. So
maybe use a concrete example. For example, congruent versus incongruent, like a Stroop task, right? So
okay.
We have two tasks. I mean, each task, two conditions. Each condition will have multiple trials. Well, the current approach, I mean, at the individual level, I mean, we assume usually adopt a canonical, right? Assume the hemodynamic response, fix the shape, fix the peak location, right? So 50 trials, suppose, then we assume all the trials share the same response magnitude and the shape, even though in reality that's not the case, right? So that's one thing. So then we estimate the brain response at the condition level, not trial level. So we get it to one for each condition, incongruent versus congruent. So then you go to group level. Group level, then we get the contrast between the two. Then you just do one sample t-test at each voxel. So then immediately then we have the multiple comparison problem, because each voxel is modeled alone. There's no information shared across those voxels. We assume they have no commonality across those voxels. That's why we have this multiple comparison problem. So I was saying, at least conceptually, we can just build one model instead of one voxel per model. At group level, for example, we just ignore the individual level. So that immediately the traditional approach with a lot of information, because we do even before we build the model, we already know the incongruent versus incongruent. We know roughly the range of the both response. We already know roughly we can approximate with a normal distribution. Those two pieces of information are useful, but not in the current model approach.
Oh, really? Okay.
Yeah.
Okay.
So that's why in the end, the penalty is so heavy. So people consider the cluster approach is rigorous. No, but because of that assumption, that prior information is not utilized, that's why the penalty is so heavy. So that's why the current, whenever you submit a paper, the reviewers will very picky about the voxel p-value of the cluster, whatever the adjustment. So that's why this is overly stringent, overly conservative. That's why the thresholding from this perspective is problematic.
Yeah, everyone has their heuristics, because if we have data and we change the p-value just a little bit, or the clustering heuristics, and it results completely change, I wouldn't want to publish that. And so I have my own sort of sense of like, okay, well, if this is so dependent on this, that it's not something that I feel is robust. And so that's sort of my own way of sort of making this modeling approach. But yeah, so you're talking about sort of maybe formalizing this process a little bit more.
Yeah. Let me go back to, you brought up the hemodynamic response, right?
Yeah.
For a long time we already know the hemodynamic response varies a lot. Daniel Handelberger's paper 2003 already pointed out there.
Oh yeah, many papers have.
Right.
It varies in latency and shape and
exactly.
On a voxelized basis, all over the place. Right.
Right. Exactly. So that approach, not that approach. The dominant approach is the so-called canonical.
Let me back up a second. Sorry, I just want to correct myself here. The hemodynamic, the neurovascular coupling certainly might change, but it probably doesn't. It's sort of like maybe indicative of the underlying neuronal signal that changes the hemodynamic response. That might cause a difference in the signal. So anyway, but the hemodynamic response itself also might vary, but to me that's less of a concern than information in the width and latency that could be neuronal. So that could be so the neurovascular coupling also might vary, but I'm a little bit less worried about that than I am, about capturing the variation. Anyway, sorry, go on.
Yeah, that's a good point. But the data we have is a both signal, right, from the scanner. we can't. It's difficult to parse.
Right.
What's a neuronal versus the carbon?
Exactly, but I just want to make sure we don't say that. Oh well, neurovascular coupling is so different, then all bets are off, and even inferring what neural activity is. I definitely wouldn't want to say that. But you're right. There is this ton of variation.
Right.
And we apply these models, and even with correlation analysis, even with looking at one area versus another, not a lot of people allow the functions to shift in time. And so you're underestimating your correlations just by not allowing them to shift, and you're not pulling out that latency information. Anyway, go on. Sorry.
Yeah, Western, that's even more problematic. But let's focus on the hemodynamics for task-based.
Yeah.
So we know it varies a lot, but the typical modern approach is to adopt the canonical, but canonical is fixed. So the peak occurs at 5 seconds exactly, right? So you have this recovery, the length, the deep, how deep the undershoot is, right? So because that modeling approach is simple, you only use that one curve to capture everything. But the downside, you may miss a lot. Well, to what degree, but we don't know unless we try to estimate it. So the recent work we did is that totally abandon that approach to just extract the hemodynamic response from the data itself. So that's, not if at the individual level, that approach has been around for a long time. Actually, probably right at the beginning. That's called the approach I call the leader spine, but different software packages using different term. In SBM, they call it FIR, finite impulse response. In AFNI, we call it TENT, right? It's just different jargons. But it all basically share the same thing. We just estimate the hemodynamic response from the data itself. So that at the individual level, that's available. But at the group level, how to handle that's a difficult situation. So that's why the recently we explored the approach at the group level. So in the end, we demonstrate that the traditional approach miss quite a amount of information, the sensitivity,
Yes.
simply because you lose the sensitivity because of the inflexibility, right?
Yep.
So especially the peak is very sensitive. If it's because the peak is lateral, relatively lateral, if the peak if it's earlier than the canonical curve, then you're going to definitely underestimate the response magnitude.
Okay, but people would argue though that, I mean, this is, you bring this up in your paper, that you have to have a model. The data might be too noisy to model on a voxel-wise basis. I mean, how do you know that you're not overfitting, or how do you actually do balance this, dealing with the noise
Yeah,
and
exactly. That is challenging. So there are technical approaches. One is the regularization. I mean, you don't only fully trust the data, right? So you use your prior knowledge. So that's basically that's one way to do that. So there are still some challenges, but so far I think we have I think relatively convincing, and it validates what you mentioned earlier, Javier's result, right? So that is 100 wrong block design. That
Yep.
was at the individual level and the block design, right? So the signal was strong. So recently we did this at the group level using the Stroop task, and it's an event-related design. So it's basically, it shows pretty much the whole brain is in, you have the both signal. I would not say it's I mean, hemodynamic response or not. That's a question, because even in white matter, you see the both signal. Whether that's a neural activity, definitely that's a little bit questionable. But at least you have the signal. That also collaborates. I mean, aligns well with some groups like John Gores in Vanderbilt, right? So their group have advocated the idea of both response in white matter.
So it's the white matter. So for instance, the reason why they see that is because the hemodynamic response shape might be a little bit different, or so just to take a side step a little bit, we looked for white matter activation in Javier's data, and we see things, but the problem is there. I mean, it's not a matter of detection, it's a matter of interpretation, because white matter always is somewhat partial volumed with gray matter a little
Right.
bit, unless you're absolutely sure you're like in the corpus callosum or something. And we see things, but we can't say for sure it's white matter, just because there's some partial volume in with gray matter that could be. So we have to do better studies at higher resolution. But you're saying that you did this with event related with the Stroop task, and using the spline fitting on a voxel wise basis, and you were able to pull out activation. And yeah, okay, all right, that's
Yeah,
cool.
yeah. Well, it still remains to be seen whether this can be, I mean, convincingly proved or not proved. I mean, supported by more data. So I'm looking forward to try this out in more data. So that it is an interesting result.
So what paper was? So that's the paper.
In your image, I think hemodynamic response is not just magnitude. I think something like that.
Yes, yes,
So there's basically a lot of room for improvement in modeling. I mean, without reporting in your imaging.
yes.
Right.
That's Neuroimage in 2023. Your
Yeah,
first
10 to 3.
author,
Yeah, yeah.
improving detection sensitivity through capturing hemodynamic profiles. So yeah, all right. And it's just yeah, and that's actually a really good point. But I think I just want to convey a practical message to people then. So if they have data, they're not getting a response that they expect. Are there tools in AFNI, for instance, that could do so? Does it do a voxel wise constrained sort of spline fitting? And can you map? So I always feel like if you do spline, then you fit and it's smooth. But I kind of like to even, like people have Buxton models of hemodynamic response, they have a double gamma variant. It'd be nice to actually sort of extract, not only look at the variation, but be able to map some aspects of that variation, like things like width or things like, some other parameters that describe the hemodynamic response. If you account for the variability, it'd be nice to keep that information and map that as well. I don't know if there's something in AFNI that does that.
I wrote a program to basically currently estimate the hemodynamic response at both individual and group level. But like the hemodynamic shape characteristics, like latency, peak location, that I think in the paper we did show some of those features. We do have, Paul, I think Paul Taylor wrote some script, Python script that can help to extract those features. So that's definitely something that's needs to be a further exploration. That depends on, I'm only good at modeling, but that depends on from the neuroscience perspective. Those features, what do those features mean, right? So the latency or undershoot, for example, how deep the undershoot is.
Yeah.
So
that's all information that I really do think that this is the beauty of AFNI right from the very beginning, is that if you have at your fingertips this information, initially we don't really know what it means, and we may not know what it means, but if we start looking at it and being able to access it easily, then we can start to figure out what it means a little bit more when the field gets pushed forward. So, yeah. Anyway, sorry, I'm going all over the place here, and I'm sort of bringing it to sort of a practical level. So let me just so basically the message there is that the hemodynamic response, I really do feel that, and so on a practical level, you would agree, from reading your papers, that the power of your studies can be improved by being a little bit more flexible, looking at as far as modeling the hemodynamic response. So.
But it's still a challenging because what the hemodynamic response we estimate, still we don't know how is that related to your activities. Right. Because we don't know how to partition the both signal, right, into your activity plus vascular components of physiological.
But that's where the interesting part begins. It's like you see a latency, you think, oh, is that hemodynamic or is that neural? Yeah. Let's modulate the neural timing and see if it's modulated as well, or all kinds of. If you have that information easily accessible, it seems like you can. That's how the science gets progressed. And so trying to create tools, and this is what AFNI has been great about, is creating tools to make this accessible. I think is great. Another thing. And I know we're coming up in the hour, but let's just go a little bit longer here because I just want to make sure at least we cover a few things just briefly. There's a couple of things that maybe there's one point that sort of made me pause and think this is a good point that I don't think is brought out, where you talk about the number of trials. And in your paper, published in 2022, hyperbolic trade-off, the importance of balancing trial and subject sample size in neuroimaging. And there, I think you bring out the point that, and a really good point, is that cross-trial variability is an order of magnitude higher than between subject variability. So just that statement alone is a little bit surprising, even to me. And then the argument then from there is that it really benefits from having a lot of trials per subject. You have to consider that point in as opposed to saying, oh, we have 100 subjects. You have 100 subjects with only a few trials, then that's not really useful. Is that your point that you're trying to make there?
This is quite interesting, and it is surprising to me too. Let's reflect what we usually do in fMRI data analysis, right? So we analyze at the individual level. We make assumption all the trials have the same response magnitude, same response shape and magnitude, right? So when we go to group level, basically just average those individuals. Then immediately, because the group results are more visible, and the statistic directly comes from the group analysis. So that's why people think the number of individuals, the participants are important. When people talk about sample size, like ABCD, UK Biobank, or whatever, even small studies, we always focus on the number of participants.
Yep.
We don't talk about the trials. Well, I don't know how generalizable it is, but usually we think individual differences is the main thing we care about. We are different, behavior-wise, personality-wise. We are so different. For each individual, you may think cross trials not much a big deal, right? So look at the simple example, like we are talking about a soup task. We just repeat the same thing. I mean, congruent. Let's focus on congruent. Just repeat the same thing. We respond with some within, for example, 1 TR. We need to respond as quickly as possible. That reaction time in itself. Suppose we have 50 trials. If we look at the cross-trial variability compared to the cross-individual variability, which one is big? Well, surprisingly, within individual variability is a few times larger than cross-individual variability.
Wow.
Well, this is just simple response, right? Well, not even we don't even talk about the both response, just
Right.
simply reacting time itself.
Yep.
That variability, just that's behavior, not both response.
Yeah.
That we also say that the within individual variability is a few times larger than cross-individual variability.
Yeah.
So it was stunning to me to realize this.
Yeah.
So
Yeah.
if we take that into consideration, I mean, if we incorporate that into the model, that's what that paper you mentioned about 2022, then you realize the trial sample size also matters, almost as important as the individual, the participant sample size.
Yeah.
So once we realize this, then you can manipulate the two sample sizes. They follow pretty much like we call it hyperbolic. Is if you draw the curve, they do those variables, trial sample size versus the individual sample size, they follow a hyperbolic relationship. So you can play with those two. Basically, you leverage the two.
Yeah.
So you don't have to focus on one, just the participant sample size. You can also increase the trial sample size, achieving similar goal. So there are some sweet spot. Then you make those two roughly equal.
Yeah.
That would be more efficient.
Yeah. And how do you calculate? How do you do that? How do you determine? How do you make them equal?
Well, when you design experiment, you need to think about how many trials you. Well, of course, there are practical issue. The participants may have tolerance in the schedule how long, but you can break into multiple rounds, multiple sessions, right? At least that's a angle you can focus on. I mean, it's increase the number of trials.
Yeah.
You pay less money, right? You can, cost is less than increase the number of participants. So from that perspective, it is something worth considering at least.
Yeah, and I think it's sort of along the lines. I mean, people might argue, well, we do as many trials as we can within the session that we have, and I just have been talking with people from WashU and whatever, the whole idea of deep scanning. There's many other reasons for doing that, but this idea that you have an individual that you scan over and over again and get more trials out of them in this regard to fully characterize them a little bit better. That's sort of in agreement with what you're saying as far as that's concerned. I mean, there's many other reasons and interesting scientific reasons to do deep sampling, but
right.
But purely statistically, it seems,
Even the cross-trial variability, why it's larger than cross-individual variability, that in itself, I mean, as a statistician, I cannot answer because this is empirical result. So that from neurology perspective, probably it's something interesting.
Yeah.
I don't know how to address that, but that's something in the future. I mean,
Yeah.
both. This is not just the neuroimaging. I mean, not just fMRI. I mean, I was talking about behavior. Reaction time itself clearly demonstrate that the within subject variability is a few times larger than cross-individual variability. That's a psychometrics. That is within years we realized that.
I can understand reaction time where you might have a wide distribution, but there's certain things. I mean, it's important to, like for instance, getting the percent correct on something that might be a little bit more stable. I mean, it all depends on the task and the
Sure.
measure.
Right. Yeah, exactly. But this
Yeah.
is a simple task, repetitive, right? You will respond to pretty much a similar trials. Those are simple tasks, right? Just congruent and incongruent. That's
Yeah.
yeah,
That's interesting. That's
yeah,
interesting.
yeah.
So that's, more to think about in that regard. So, all right. So let me just uh, sort of just to try to summarize. I mean, it's hard to even summarize what you're saying completely, but if you were to summarize sort of like the general stance of what you're trying to say about with all these papers of, you know, the thresholding, the modeling, the reporting, we didn't even get to reporting the actual effect size versus the statistic, and also the role of multiple trials versus multiple subjects. How would you summarize this as in terms of and also not only how would you summarize this in terms of a philosophy that people should be aware of, but are you working on making tools that make it easy for people to try these approaches?
I think to summarize, I mean, there are a couple of things. I think modeling philosophy perspective is we build a model. Model is just a data machine, right? We use the models to simulate the real world. I mean, the physics or other scientific fields, they also build models. But the statistical model is a little bit unique is that we incorporate the randomness, right? So whatever we can't explain is just the sweep under the rock of the noise. We call it noise. But that's, you can call it art or call it science, because art is trying to extract the information.
Yep.
You can understand to some extent the real world, to simulate the real world. But there are two directions. One direction, we have the available tools, t-test, regressions. We have the data, we just force the data to fit the model. That's one approach, one direction.
Yep.
The other approach is maybe more, challenging, is that to force the model to fit the data as close as possible. That is something we need to work harder, especially for statisticians. That's something because the tool, those tools in the box, it's you can pick up to force that the data to fit that, but that's not necessarily a good approach under all circumstances. So
Yeah, and
that's a
that's
modeling philosophical perspective.
yeah, and that really is an important thing that people should think about is that the whole art is, as you're saying, is sort of like casting a wide net. You don't want to get too many things in the net, but you want to have it selective but flexible. Because there's still a lot we don't know about the noise. There's a lot we don't know about the signal, and you don't want to throw it away too quickly. But at the same time, you don't want to take in everything. Uh, so there's an art and there's a balance of this as the field progresses, and I think that's exactly that's the challenge. I mean, that's
Right.
actually the challenge.
That is the challenge. So another way aspect I want to summarize is that what's the role of statistics? Is really you should use this statistics to police the result reporting process, to play a role of gatekeeper? I tend to disagree with that. I think statistics is just a tool. A tool give us some piece of information, but that's just one. There are other, as a scientist, you have the domain knowledge. We should combine to integrate, to synthesize all the information. Not statistics is just one aspect. There are other things, right? So for brain, we have anatomic structure, our literature. It's a plus in the end. We don't need to make a decision. Even we make a decision, even a traditional statistic, false positives. But there's also another aspect, false negatives. Why do we solely rely on false positives, fully ignore false negatives? That's another thing we didn't talk about, but that's when we make a decision, whatever decision, there's two sides of it, right? So that's why I think the approach we suggest, the highlight but not high, I think
Yeah.
that's keeps a counterbalance to achieve that goal. Don't, it's you let the statistics play a gatekeeper. Instead, just synthesize. You want to highlight it. Yes, you can emphasize whatever you feel is the evidence is strong. You can do that. That's the highlight part. But we don't have to hide the rest. We just this is aligned well with the open science movement, right? So
Yep.
full without transparency, full without reporting. So this is, I think this is more, at least I personally consider as a better approach. So those
Yeah.
are the two things I want to summarize. What do we have discussed?
Oh, that's perfect. That's perfect. And I recommend everyone take a look at Gang's papers. In the last, 2023 in neuroimage, 2023 also in neuroimage with bold responses more than just magnitude. Also 2022, the importance of balancing trial and subject sample size. And also the last one in neuroimage, also 2017 is statistic value all we should care about. But also you had a paper in, if I Aperture Neuro. So I'm a plug for Aperture Neuro, which was a nice summary. There was actually a really nice figure in Aperture Neuro too. And this was sources of information waste in neuroimaging, sort of a summary of some of these other papers in some sense. And there was a really nice figure in which you went from, where you showed the trade-off between information reduction and ease of interpretability. And so, you have raw data, you have all the information there. It's impossible to interpret, but then there's this trade-off between how digestible it is versus how much information you reduce, and the trick, the challenge is finding the right balance in this. And I think most people just want to do the right thing, but the fact is we're all struggling with these two sets of curves, and this, people should be aware of this, is that, hey, do the models as best you can, but at the same time, know that there's more there, and how do we balance that? So that was a beautiful figure, by the way, I thought. All right, so so thank you very much, Gang. You gave sort of philosophical advice in some sense and some practical advice. Obviously, there's potentially tools in AFNI that you keep on growing as far as that's concerned. Is there a plan for? I mean, you write about this, but is there a plan for? And how would you prioritize this plan for implementing these in AFNI or in general? I mean, there are sort of elemental tools that would be good, but sort of you're pushing the philosophy, but also people just want to know, how do you try to do what's in your papers? Do they just need their MATLAB code or there are things?
Currently, I'm trying to improve. A challenging part is how to estimate the hemodynamic response at the trial level, especially for eventually design. That's very challenging. It's related to the issue we're talking about, because cross trials are a lot of variability. This for especially this for those people who work in machine learning, because they or classification, they need to how to accurately estimate the trial level response. So that's something we are currently working on. This is computational intensive and very challenging, but we have made some progress, but still a lot of work to be done. So that's one thing I have been working currently. We are using multiple tools and programming. Especially, I usually use R, not MATLAB, but this involves like Bayesian modeling, so that it also gets the standard programming language involved. So that's another aspect.
Well, good. All right. Well. Thank you very much. Look forward to seeing what work you're coming out with, and I'm definitely making a note to. Your office is right down the hall, and so I should talk to you a lot more to learn something. And well, thanks again, Gang. Appreciate it.
Thank you, Peter. Thank you for having me, and had a nice conversation. Thank you.
All right. Well, thank you. Thank you.